Okay, so today we are looking at vectors and introducing basic characteristics of vectors. So the big idea is a vector is a movement in the xy plane in a particular direction. So looking at the big idea for vectors, we can represent some physical quantities with vectors, and one of the best physical quantities that we tend to represent with vectors are things like velocity. So for instance, keep this going. Velocity is a vector quantity. It differs from speed, which is a scalar quantity. So for instance, if we move in a particular direction, and this is our velocity in this direction, whereas speed doesn't matter which direction we're going in, we can move around in a certain pattern. It talks about the overall distance covered divided by the time taken to do it. So when it comes to scalar and vector quantities, when we talk about distance, we can split that into a scalar and vector version. So for instance, distance is a scalar quantity, whereas the vector version of that is what we call displacement. Let me give you an example. If I start here at this particular point, and I move in this direction by 3 meters, like this to here, then I have a displacement of 3 meters in this direction, I have a distance covered of 3 meters. If I walk back 3 meters to here again, now my displacement is 0. I have been displaced by 0 meters, whereas the distance I have covered is 6 meters, because I've been there and been back. So if we're measuring the distance I've covered from this point, it's 6 meters. It's scalar. It doesn't matter what direction I moved in. Whereas if we're measuring the displacement I've covered in this one, it matters which direction I've moved in. So for instance, I can move across here in this direction to about here, which is maybe 4 meters, and I can move across here in this direction here, which is maybe 3 meters. My displacement now is 5 meters. I'm 5 meters from this direction here because I haven't moved in a straight line. I moved 4 meters in one direction and then turned 90 degrees, moved 3 meters in that direction. And if you're familiar with the Pythagorean triangle I just made, that displaces me 5 meters in that direction. So the difference between what a vector is, it is a particular magnitude with a specific direction. It's a magnitude in a specific direction. That's the definition for a vector. And we can define a vector like this. So we have a couple of representations you'll see. This is one way of denoting a vector. You can't draw bold with your on your page with your pencil, so we do a line above it. We can represent it as a row matrix or a column matrix, or a row vector or column vector. It's the same thing. You'll also see it written with this bracket. Can sometimes be used. I prefer not to use this one because it confuses me a little bit with hypertext markup language and that type of thing. So I'm not into it. Okay, so we have an example here of a vector, 5, 12. That means we move 5 along in the x direction and 12 up in the y direction. How would we find the magnitude of this vector? So if we wish to find the magnitude of this vector, we have a vector which is, this diagram doesn't work very well, it's 5 across in this direction, and it's 12 up in this direction, and that makes a right angle triangle. So how could we find the length of this vector? The magnitude of the vector is here, the length of this line. Zinedine. Sorry?
I gotta go.
You get to go.
Yeah, so Pythagorean identity, a squared plus b squared equals c squared. So the square of 5 is 25, the square of 12 is 144. Added together is 169, and the square root of that is 13. So the vector has a magnitude of 13.
Thank you. It's not the Pythagorean identity. That's trigonometry. But you did get overexcited and give me the whole solution. Thanks for that. So what Zinedine is saying is we can use the Pythagorean theorem
And we can have the length, that length squared plus this length squared is going to give us root 169, which is going to give us 13. Excellent. You can use the distance formula for this one, but the basic formula, the formula for the magnitude of a vector is equal to, x squared plus y squared.
If it was a three-dimensional vector, x squared plus y squared plus z squared. Just keep adding another
Component.
three-dimensional vectors. Because this is a vector in a plane. If you want a vector in a space, then you need three-dimensional vectors.
Okay, have a go at finding the magnitude of this vector. Okay, so let's have a look. The magnitude of this vector is going to be the square of 4 squared plus 8 squared, which is going to give us the square root of, 16 plus 64, which is root 80, which is 4 times 4 times 5, which is 4 root 5. Right. I see 80 as 4 20s. Have a go at finding the components of vector u using the information given here. You can work together in pairs. So we want to create the vector u. This is going to be the magnitude of u multiplied by the cosine of theta sine theta. And there's the formula for this. So this gives us 15 cosine of 60 degrees sine 60 degrees, which is going to be 15, what is the cosine? It's a half, and this is root 3 over 2. So this is going to be 15 over 2, 1 root 3. We can write it like this. I think this is the most compact version of writing it. Or we can write it as 15 over 2, comma, 15 root 3 over 2. And write it like this. So we could write it as any of these three representations. There isn't a correct simplified version for this one. I like this representation here. We can move fluidly between the different ones as we wish. Okay, example 3. We're going to need to use our calculator for this one. Have a go at this one on your calculator. All right, so find the components of vector v. What we want to do, so we'll use the formula. V is equal to 6 bracket cosine 160 sine 160. Take out your calculator in your hand. Sorry. Let me stop my share here. Can I jump in with this one? Okay, so on your calculator, take your calculator out. Take your calculator out. Press the templates button next to the 9. So you find the templates button here next to the 9. And if you look on the second row, 1, 2, 3, 4 in, you'll see a little column vector. So we can press that. Into this, we can write cosine 160. And we can write sine 160. And then times it by 6. We should, if you get this type of an answer, just press Control Enter and you'll get a decimal answer. Okay, let me come around and help. Does anyone need any help on the calculator on that one? Okay, so 6 times, that's the templates button. And then cosine 160.
Of course you need to change it to the design. So move. The brain is like no.
So maybe we just make it clear on this one, and then we edit the matrix of those. And then let's define shape and size of the matrix. So we have 1 by 2. And then all right, let's have a look at the next question. Okay, so next up we're looking at the idea for scalar multiplication. So you can take a vector and you can multiply it by a scalar value. A scalar value is a number without magnitude or direction. So when we're multiplying by a scalar, we multiply each of the components of the vector by that scalar. So to show you as an example here, we're going to multiply this number here by a scalar. This is going to give us 2 times 3 and 2 times -2. So that's going to give us 6 minus 4. Here is our vector. Have a go at the second one for yourself. Oh no, wait a second, sorry. I have some more to talk about. I have to draw the vectors. So our first one is 3, 2. So if I'm going to draw a vector, it's important to know the geometrical representations of them as well. So our first one is 3, minus 2. So it doesn't matter where we place the vector on the plane. So if I start my vector off here at this particular point, we need to go 3 across and 2 down. It's going to give me, it's going to give me this. This is the vector u. So then we multiplied it by 2, and we got the 6 minus 4 as our vector. So
Doesn't matter where we place it on the plane. If I start here and I go 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4.
Sir,
Yes.
vector, it's an arrow, so it goes infinitely, so isn't that the same?
No. It doesn't go infinitely. It has a magnitude. Very important about a vector is that it has a magnitude. That gives it a very specific length.
So what is the arrow?
Because it shows that, like, going
Because we need to know the direction. It's not a segment. It's not a line segment. It is a vector. It's different to a segment. A segment would be a length of line in the geometrical plane with a specific length but no direction. A vector has a specific direction. The direction is very important. Sorry? No, a line has an infinite length. A vector or a segment don't have an infinite length. They have a very specific length. The length of this is, we can calculate. That's what we've just been doing. We've been calculating the magnitude of the vector. That is the length of the vector. What do we notice about these two vectors?
One's half of the other.
Yeah, so it's twice as long. When we multiply by a scalar, it doubles the length.
Why can't we like draw it upside down? Would that be allowed because the direction changes? Like let's say
It's not the same vector.
but how do you like know it's facing that direction?
The arrow.
As in like when you draw the triangle, does it have to always be in that orientation?
Yeah.
It has a very specific orientation. So if we see in the orientation here, it says to move 3 across and 2 down. So no matter where you place your starting point, it says so we can take the same vector. Let's pick a starting point here. So if we put the starting point here, then the vector says move 3 across and 2 down. It's going to become this line here. This is the vector u. And you see from where you start to where you finish what the vector is. We can give the vector endpoints. So this is from A, B, and this is from C, D. So we can have, both of these are going to be different start and stop points. So let me just plug in over here. So we could also say that the vector AB is equal to the vector CD is equal to the vector U. Okay, have a go now at doing number 2 and sketching it on your axes. So pause for a minute. All right, so for the multiplication of this vector by the scalar minus 2, we are going to get 2 times 3 gives us minus 6 and plus 4. So this would be our result. Let's have a look at this. This is quite interesting when we look at this vector geometrically. So we've got 3 minus 2. So 1, 2, 3 minus 2. This is still the vector u, but when we multiply by the scalar this time, we get minus 6, 4. So let's have a look. Let's start ourselves off here. So now we get this vector. This is minus 2u. If we compare it to the ones we did earlier, when we look at the vectors and we multiply by a scalar, what do we notice happens? There are 2 important things that happen, or 3 important things that happen. What are those important things? Discuss with the person next to you. What are the 3 important things we can see when multiplying by these scalars? What does that mean?
Same ratio.
What else? When?
Not the direction change, but the starting point change.
No. I can place the starting point anywhere. It's a vector. The vector has no specific starting point.
The direction didn't change.
The vector just describes a journey in the Cartesian plane. And what's the obvious one? Yeah, the size. So we have three things. We have three things when we multiply. We have an enlargement factor, whatever our scalar is. So an enlargement, a factor of half will shrink it. So we get enlargement factor by the absolute value of lambda. We get a change of direction. We get a 180 degree reflection or rotation, change of direction when lambda is less than 0, when it's negative. And 3, the important one, is no change in direction. Or no change in direction. Well, not direction. So any two vectors, if you multiply a vector by a scalar, it will still be parallel to the original vector. Notice these lines are all parallel. So there's no change in the slope. All of these lines are parallel. No matter what vector, where I place the vector as the starting point, and if I multiply by a scalar, positive or negative, it's not changing the slope. They're all still going to be parallel. That's really useful as we get into this topic. Okay, last up I think is vector addition. Pretty straightforward. When we add two vectors together, we are going to get this as our result. So showing you here with my example, we've got 3 plus, this is going to give 3 plus 2 over minus 2 plus 5, which gives us 5 over minus 3. Oh, sorry, 5 over 3. However, let's look at this result graphically. Sorry, let me try that again. Let's look at the result here graphically. So our first vector is 3 minus 2. This is our vector v. So we can place this anywhere we want. I'm going to place it starting at the origin. We go 3 minus 2, and we get this as our vector. This is the vector v. Then we have the vector u, which is 2, 5. So I'm going to place them tail to toe, head to toe, and we want to go across 2 and then up by 5. So we're going to go to here. So this is the vector u. If I draw the resultant vector, this is a very important result. If I draw the resultant vector and read the resultant vector off of the graph, what is this green vector? Sorry? No, what is the components of this vector?
It's a triangle.
No, what are the components of the vector?
V and U. No.
No. Can you count how many across and how many up?
3, 2 up, 1 across.
3 up and 5
No, 3 across 2 up.
Wait, no, wait.
1, 2, 3, 4. How many across?
5.
So this is 5, and how many up? 3. I didn't believe that was hard. Our resultant vector is v plus u, 5, 3. And if we look at the algebraic results, when we added them, that's the answer that we get algebraically. So the graphical result is very useful for us as we get on into this topic. We can see how it's happening here. All right, to finish off, is this the last ones? Yes. Let's finish off with these two. Have a go at these two questions for yourself. I think that's it. All right then, so we've got two vectors here. We need to find the magnitude of u. So this is going to give us the magnitude of u is equal to the square root of 4 squared plus 2 squared, which is equal to root 16 plus 4, root 20, which is 2 root 5. In our second one, we need to find 2u minus 3v. So 2u minus 3v is equal to 2 bracket 4, 2 minus 3 bracket negative 3, 5, which is equal to 8, 4 minus negative 9, 15, which is 17 minus 11.
So isn't it 9 negative 15?
It's minus and then a negative number.
No, we don't distribute the number.
Oh, you don't use it.
I could distribute the negative, but I didn't.
Why?
Didn't fancy it. I saw it more as subtracting by 3 times v.
Did you do it both ways though?
Yeah, it'll come to the same result, obviously.
Sir?
So it would change here at this point. You'd get 8, 4, and then you'd get, this would change to a plus, and you'd get 9 minus 15, and it would still come to here. It doesn't matter whether you see the scalar as being minus 3 and that you're adding, or whether you see the scalar as being 3 and you're subtracting. The result would be the same. Okay, that is it for today. Have a go at the classwork on the Google Classroom.